it's Greg again. Today we're going to talk about implicit differentiation. So there's a difference between there's this. I'm actually about to explain the difference between regular and implicit. Explicit relations are equations where y equals some function of x. Like we all know that this quadratic function, y equals x squared plus 9. We can solve it easily, graph it easily, find zeros if there were any easily. But implicit relations are equations in which both x and y appear on the same side, similar to the equation of a circle, like x squared plus y squared equals 9. Now we all know that this is a circle centered at the origin with a radius of 3. So I use the same numbers just so you can see the difference between explicit and implicit relations and the differences just right there that exist between them. So our problem, we can't solve these like we would normally. So our problem is to find the derivative dy dx of that implicit relation. We have to find the derivative with respect to x for a relation whose equation is written implicitly. So for this one, we'd have to find the derivative. We're basically just taking the derivative of this equation in a special way. So you're solving these differently than the implicit differentiation. Now I can just rattle off what the derivative of this function is, being 2x squared. But this one I can't do automatically since it's implicit. Now the steps of solving this one. First, we have to differentiate both sides of the equation with respect to x, which we're going to go through. Obey the chain rule by multiplying by dy over dx each time you differentiate an expression containing y. Now this kind of tripped me up because I was looking in the book, and this was very confusing to me because I learned it differently. But dy over dx is the same as y prime, or the derivative of y. Third, we have to isolate dy over dx by getting all of the dy dx terms on one side of the equation and all other terms on the other side of the equation. So we're basically just solving for y prime or dy dx, so you want it to look like implicit. And then next we factor if necessary and divide both sides by the coefficient of dy dx to find the ending answer. So now we're going to go through an example. This example is actually from in class. X squared plus y squared equals 25. We're going to calculate values of y when x equals 3. So we know that x squared plus y squared equals 25 is a circle centered at the origin with a radius of 5 this time, instead of a radius of 3 like the example over here. So since I want us to find values of y at 3, first what we're going to do, I wrote the equation again, and then we just substitute 3 for x and then solve for y. So that's pretty self-explanatory. So and y squared ends up being equal to 16, and 16 actually has two square roots, positive 4 and negative 4. So we have to use both of those. So the points we get for where the y values we get for where x equals 3 are 3 4 and 3 negative 4. Now I drew our circle on a graph, and 3 4 and 3 negative 4 are points of tangency where the line only touches the graph at that one point. Now down here, we're actually going to solve for the slope of a line of tangency. So what I did is that there's the original equation, and then I took the derivative of it with respect to x, so the derivative of x squared is 2x. The derivative of y squared would be 2y dy dx. Based on up here, when we have to put dy dx each time we take the derivative of an expression containing y. So that's what I did there, and then I subtracted 2x, so I have 2y over dy dx equals negative 2x, and then to isolate the dx or dy dx, I divide by 2y. So we end up getting dy dx equals negative 2x over 2y. The 2's cancel out, so it ends up being dy dx equals negative x over y. Then we can substitute in x and y values, which ends up being negative 3 over negative 4 equals 3/4. So we in that 3/4 is a slope for one of our tangent lines. So we have the slope and we have the point. The point I used was 3, negative 4, based on that. The negative x over y, the negative on the negative x over y goes to negative 3, and I used the negative 4. So therefore I used the point 3, negative 4. So our slope is 3/4 and our point is 3 comma negative 4. So from there we can just write our equation for one of the tangent lines. Y equals 3 over 4 parentheses x minus 3 minus 4. And if you notice up here, that would be the slope of the lower tangent line, based on the point we used. The upper tangent line would most likely be negative 4 over 3, I believe, because it's the line goes down from left to right, and it goes to that point 3, positive 4. Okay, and on to the next problem. This one's a little bit more complicated, but it's the same theory. Y to the 4th plus x to the 3rd, y to the 5th, minus 2x to the 7th equals 13. So we're going to start off by taking the derivative of everything. The derivative of y to the 4th is 4y cubed dy dx, because we have to put dy dx because of the y there. X to the 3rd, we leave the x there. That's a constant. We actually have to use chain rule here, because x cubed and y to the 5th are being we have to use product rule, which is first derivative second plus second derivative times first. So the x cubed sits, and then the derivative of y to the 5th is 5y to the 4th dy dx, plus, and then on the next term, because first derivative of second plus second derivative of first, the y to the 5th sits, and then the derivative of x to the 3rd is 3x squared. So that is all one term as I have it written. And then the derivative of 2x to the 7th is 14x to the 6th, and that equals 0 because there is no derivative of a constant. So next I just multiplied everything so it all, to get rid of the parentheses, so it all becomes one term. 5. The only thing that changed was the middle section where I had to use product rule, which becomes 5x to the 3rd y to the 4th dy dx plus 3x squared y to the 5th. So otherwise everything else is kept the same. The next thing I did was move the 3x squared y5 and 14x to the 6 to the other side to separate the dy dx terms from the just numerical and xy terms. Then I took the dy dx out. I divided by the dy dx, or took it out. So I have dy dx times 4y cubed plus 5x cubed y 4th equals 14x to the 6 minus 3x squared y 5th. Then I divide it, and then to get the dy dx by itself, I divided by 4y cubed, 5x to the 3rd, y to the 4th. So then this equation is what you get when you divide. Now next, that's actually our answer to this one, because it can't be simplified anymore because of the addition and subtraction signs that sit between the terms. Our final example is a trigonometric. It's actually a trigonometric function, sine xy. So same thing. The y sits. You have to put d dx because the y is already there. Sits because the y is sitting by itself right there. There's already the y, and the y is also on the other side, so you have to put d dx, and becomes dy over dx equals cosine xy. Now that's actually chain and product rule, so we get x times dy dx plus y, because of this y right here with the d dx. Now dy over dx equals x cosine xy plus times dy dx plus y cosine xy. Now that's just simplified. And then from there it's basically just taking out dx and dividing by dx, and taking out dy dx, then dividing by 1 minus cosine xy to the y cosine xy on the other side, and then there's your final answer. Alright, that's it for implicit differentiation. Bye.